In the previous video, we defined right-hand and left-hand limits. So recall that the limit as x approaches c from the right is equal to L, provided that if h is infinitely close to c but bigger than c, then the standard part is what the limit is. And from the left-hand limit, we've got to be, again, infinitely close to c, just like a limit. But now we're strictly less than c, and again, the limit is the standard part of the function. So left-hand limits and right-hand limits are just restricting our domain. So let's look at an example. Let's say we want to compute the limit as x approaches 0 from the left. So there's a little minus sign. So this is saying we're going to be less than 0. We're going to be to the left of 0. And the function we're going to take the limit of is x times the square root of 1 plus x to the minus 2. So if we're computing a left-hand limit, we want x, or we'll say h, be infinitely close to 0, but because of the minus sign here, we need to force h to be strictly less than 0. Okay, so these are our assumptions when we compute standard parts. H is infinitely close to 0. That's the limit part. We're going to get close to 0. And then the fact that it's a left-hand limit means that we want h to be to the left of 0, or less than 0. So this is equal to then the standard part, again, provided this exists, of h times the square root of 1, and I'm going to write it this way, 1 over h squared. Right, because we've got a negative 2 there. And h is infinitely close to 0, so we can't just put it in because we would be dividing by 0. This is an infinite value, but this is an infinitesimal, and so as we know, an infinitesimal times an infinite number is indeterminate. So we've got to work out what that is, do a little bit of algebra. So this is the standard part of h times the square root, and I'm going to combine these two numbers, 1 plus 1 over h squared. I'm going to turn it into one term. So my common denominator is h squared. So this is equal to h squared plus 1 all over h squared. Now I'm taking the square root, and the h squared is here, so I can bring it out. So this is the standard part. But when I bring it out, it's got to be the positive, because the square root returns the positive value. So this is h over absolute value of h times the square root of h squared, plus 1. Now, if you're scratching your head, why do I have an absolute value over there? Recall that by definition, the square root of h squared is equal to the absolute value of h, because the square root always returns a positive number. I don't know what h is. In fact, well, actually I do. It's negative. But h squared would be positive. And so the square root returns the positive value of h. So that's where that absolute value came from. And now, since h is negative, this tells me that the absolute value of h is negative h. H is negative, so if I multiply by negative, it becomes positive. So this is equal to the standard part of h divided by negative h times still the square root of h squared plus 1. Now I get some canceling there. This is equal to the standard part of negative square root of h squared plus 1, which is equal to negative square root standard part of h squared plus 1, right? Because the standard part now moves past the negative sign and can slide into the square root function, and the standard part of h is 0 because it's infinitely close to 0. So this is equal to the square root of negative. Got to carry my negative, right? There's a negative there. This is negative square root of 1, which is simply equal to 1. So that is the limit as x approaches 0 from the right of x times square root of 1 plus x to the negative 2. If we were to look at the other end, so let's look at the limit from the right. So the limit as x approaches 0 from the right of x times the square root of 1 plus x to the minus 2. Now, instead of h being negative, right, this positive there tells me that h is infinitely close to 0, but h will be greater than 0. And we know we've kind of been through this problem already, so we know this is going to show up, so we remind ourselves that the absolute value of h then is just equal to h. So this is equal to the standard part. Well, I'm going to skip a bunch of steps because this is going to be boring, but it's going to be h times 1 plus h squared. I'm going to do all this business of making under one fraction. It's going to come out. So I'm going to skip right to this step. Right? So just to make it clear, I'm skipping these steps. I'm kind of pretending I already did them. So they're kind of hidden right here. So I've done them already. I've simplified, so this is equal to the standard part of h divided by the absolute value of h times the square root of h squared plus 1. But now my absolute value of h is simply h. So this is the standard part of h divided by h square root of h squared plus 1. But now h divided by h, this ratio here, is just 1, right? This is 1. And the standard part will squeeze through like it did before, and we get that this is equal to a positive 1. Since the left-hand limit and the right-hand limit do not agree, then we know for a fact that if I were to do a straight limit, right, putting this kind of together and using theorem 1 by theorem 1, the limit as x approaches 0 of x times the square root of 1 plus x to the minus 2 does not exist, right? It doesn't exist because the left-hand limit is negative 1 and the right-hand limit is positive 1. Okay, let's look at one more example using these one-sided limits. I'm just going to compute one of them. So let's say I want to know what is the limit as x approaches 2 from the right of the square root of x minus 2. What is this equal to? Well, to compute it, we would say let's let we're going to let h be infinitely close to 2, but h be strictly bigger than 2, right? Because we're approaching from the right, it's positive, so h is going to be bigger than 2, greater than 2. So it's positive, we're going to be bigger than 2. So that's what we know about h, and so this limit is simply the standard part of the square root of h minus 2. Now we want to slide through, and that'll be fine because we know that from up here that since h is infinitely close to 2, that the standard part of h is equal to 2. So we know how to do that, and we know the standard part slides into the radical here. But there is something we need to check before we do anything, because the standard part rule says that this has got to be defined. So let's make sure that h minus 2 is positive. Well, coming back up here, since h is bigger than 2, we could subtract 2 from both sides. So h minus 2 is positive, which tells us that the square root of h minus 2 is defined. That's good. So then this is equal to simply the standard part, the square root of the standard part of h minus 2, which is the square root of 2 minus 2, which is 0. So the limit from the right exists. However, if I compute the limit from the left, so the limit as x approaches 2 from the left of the square root x minus 2. Well, now we're similar. We want h to be infinitely close to 2, and h now is strictly less than 2 because we're using here, where this is telling us the left-hand limit, so we're to the left of 2. And so this limit, if it exists, will be the standard part of the square root of h minus 2. But just like before, we've got to make sure that this is defined. So if h is less than 2, then h minus 2 is less than 0, which tells me that the square root of h minus 2 is not defined. Right? We can't take square roots of negative numbers, which means this standard part does not exist. And since the standard part of it doesn't exist, this left-hand limit does not exist. And the graph of this function will kind of clear things up. Why should that be the case? Well, if I plot the graph of the square root function, so here's my y-axis, my x-axis, and going back to thinking of algebra, this is the square root function shifted 2 units to the right. So here's where 2 is, and so then the graph of our function would be something like this. And the domain is x bigger than or equal to 2. So when we took our limit, we're letting x, in the first part, we let x get close to 2 from the right. So x getting close to 2 from the right means that we're going this way. We're letting x approach 2 from the right. This was our limit as x approaches 2 from the right. However, coming from the other direction, when we tried to go to 2 from the left, so we came from this direction, looking at the limit as x approaches 2 from the left, there's no function here. It's not defined. So we can't even ask what the limit of the function is doing because it doesn't exist over here. So the left-hand limit doesn't exist because we can't even put it into the function to try, whereas the right-hand limit, approaching 2 from the right, does exist because, and if I were to kind of get up my infinitesimal microscope here and zoom way in, so let's come here. So I zoom in here. We still have, so we're zoomed into the x-axis. We're at the number 2. And my graph would look, it would look very linear here. So it looks something like that. That would be our function there. And we see that as the input gets closer to 2, as my input gets closer to 2, my output gets closer to 0. As my input gets closer to 2, my output is getting closer to 0. But again, I can't even ask what is my function doing if I come from this direction. There's no graph over here. There's nothing that can be done. And so, again, we say that the right-hand limit exists, and it's equal to 0, and the left-hand limit does not exist, period.